Welcome to physics class. Now I am going to explain the details about gravitation. In gravitation lesson, subtopics are Newton's law of gravitation, that means gravitational force details, Kepler's laws, acceleration due to gravity, next variation of acceleration due to gravity with altitude and depth, orbital and escape velocities, gravitational potential energy and satellites, means about natural and artificial satellites. First one, Newton's law of gravitation. So that is about gravitational force between two massive bodies or any massive bodies. So definition point of view, gravitational force is the force of mutual attraction between any two massive bodies by virtue of their masses. Consider two massive bodies m1, m2. Let us suppose m1 is bigger, heavier as compared with m2. So even then, what it may be the size, what it may be the shape, what it may be the quantity of mass, any two massive bodies will attract each other. That is called gravitational force. This is explained and analyzed by Isaac Newton. So according to his Newton's law of gravitation, that attractive force between any two massive bodies is directly proportional to the product of the two massive bodies, means product of the two masses of the bodies, and inversely proportional to square of the distance between them. So that proportionality constant is g. So here g is called universal gravitational constant. The value is 6.67 into 10 to the power of minus 11 Newton meter square by kg square. So here g we are calling as universal constant, means universal gravitational constant. Universal word means it is valid everywhere, means irrespective of the place, irrespective of the medium, so everywhere it is same. So that is why we are using the word universal. It is proportionality constant and as well as same everywhere. Next, the properties. If you analyze the entire gravitational force, the properties point of view, so we will get the clear idea about the gravitational force between the two massive bodies. So here the gravitational force, if you study about any two massive bodies, it is not like a attractive force or repulsive force between two charges or two magnets. If you observe in your daily life, two magnets if you keep very near to each other, you can feel either attractive force or repulsive force. But if you keep two massive bodies very near to each other, then you will not feel any attractive force between them. Reason, this force is very weak force. So gravitational force is very weak in nature and as well as long range forces. Even though these are very weak, these are long range forces. Simple example, two magnets, what I said just as an example, if you keep two magnets very near, you can feel attractive or repulsive force. If you keep those little bit away, just 10 to 30 centimeter distance, then almost we can't feel any attractive force. But the gravitational forces, these we can't feel, but there is a gravitational force, even then the distance is in huge meters or huge kilometers. Simple example, the distance between the sun and the earth is 1 astronomical unit, nothing but 1.5 into 10 to the power of 11 meters distance, or 1.5 into 10 to the power of 8 kilometers. 10 to the power of 8 kilometers means that is huge value. Even then there is an attractive force between sun and the earth. So that means these are long range forces. And one more major point, these forces are independent of medium between them. Means even though you introduce the medium between the two massive bodies, even though medium not there, the attractive force between the two massive bodies is the same. As an example, two massive bodies at a distance in air, there is an attractive force. The same two massive bodies, if you keep inside any liquid or water at the same distance, then attractive force is the same. Previously, in between the two massive bodies air for suppose, now we introduced water in between or liquid in between them, even then that attractive force will not affect. That means the gravitational force is independent of medium between them. And for the next points with respect to diagram, here one point I want to tell you here: two massive bodies are at a particular distance, then there is an attractive force. It is a mutual attraction, I told already. So that means m1 will be attracted by m2 towards m2, m2 will be attracted by m1 towards m1. So these two forces we are mentioning as f1 and f2, but both are mutual and equal, and the force of attraction is always along the line joining the two massive bodies. That point also very important one. And further, here that attractive force or gravitational force between them depends upon the product of magnitude of the charges. If masses are huge, attractive force is high. If masses are lighter, that attractive force will be less. Next point is attractive force. This attractive force is inversely proportional to the distance between the masses. If those are very near, more attractive force. If you keep those away, then attractive force decreases gradually. And one more point, always along the line joining the 2 points that I already mentioned. And last, one more important point, these are only attractive force. In the universe, there is no repulsive force in case of gravitation. Gravitational force is only attractive. There is no repulsive force in the world regarding gravitation. Next, Kepler's laws of planetary motion. So to explain the details about the planetary motion, Kepler designed 3 laws. Those are 3 laws. First one, Kepler first law, simply we are calling as first law, that is also known as law of orbits. Second law, that also known as law of areas. Third law is also known as law of periods. Now first law. According to Kepler first law, every planet revolves around the sun in an elliptical orbit with the sun is at one of its foci. This law is also known as law of orbit's reason. This law is giving the details about the path of the orbit. You can see in the diagram the planet revolving around the sun in elliptical orbit with sun is at one of its foci. So it is an ellipse, it is having two foci. Circle means only one center will be there, ellipse means two foci will be there. So sun will be there at one of its foci, the planets will revolve around the sun in elliptical orbit. So here these are revolving in elliptical orbit means the planet is coming very near to the sun sometimes and it is going away, and it is maintaining a long distance sometimes. So it is coming very near and it is going away. So it is maintaining the fixed orbit, means whenever it is coming very near it will move faster, then only that attractive force will be balanced by outward force. So as it is going towards B, means by near to the sun at A, the velocity will be high so that it can balance the gravitational force, but at point B the velocity will be very less. Reason, here attractive force will be less, so the planet can move slow and it can cover the path. And here A and B indication, let me explain. First, here A, B, what I am indicating with the laser point, it is a major axis, and perpendicular to this axis here one more, this is minor axis. That half of the major axis we are calling as a semi major axis and it is indicated with A, and half of the minor axis, that is a semi minor axis, that is indicated with B. So here small a is major axis and B is minor axis, and here E nothing but eccentricity. So it is a major concept in mathematics. According to the value of eccentricity we can judge the shape of the curve, means according to the eccentricity value we can judge the curve is parabola, hyperbola or ellipse. So we can judge, for example, this eccentricity value greater than 1 for a particular curve, that curve is a hyperbola, and if E value equals to 1, then the eccentricity value E equals to 1, then that curve is represents parabola. So for all parabolas, that eccentricity quantity value will be equals to 1. So E value 1 means that is parabola. If E value is less than 1, so three categories: E value greater than 1, equals to 1, less than 1. So greater than 1 means hyperbola, equals to 1 means parabola, less than 1 means that is ellipse. Kepler derived the equation for eccentricity and mathematically showed that E value is less than 1 for a planet revolving around the sun. So for us only just theoretical information, so that is why I am unable to show entire theoretical data. So oral I am telling. So he derived an expression. From that expression he showed that eccentricity value is less than 1. So with respect to that he concluded that the path of the planet is an ellipse. Next one, Kepler second law. So according to Kepler second law, so about planet, here first law he gave the details about orbits, so that is why that is called law of orbits. Now it is called law of areas. Why? Because this law is giving the details about area. So for that, first definition, the radius vector drawn from sun to the planet gives equal areas in equal interval of time. That means the rate of change of area of the planet, that we are calling as areal velocity, is constant. So it is giving the details about area, so that is known as law of areas. Let me explain once again. So here see the diagram. Here sun, the planet for example revolving continuously around the sun in a particular elliptical orbit. For suppose here you can see circular dot points. So here t is the time, means planet covered from here to here it took time t. So here also to cover the distance from here to here it took time t, and here also from here to here to cover this distance the planet took time t. So here very near to the planet it moved faster, so that is why it covered much distance. But what it may be the velocity, so here you can see the radius vector drawn from sun to the planet gives equal areas in equal interval of time. The radius vector drawn from sun to the planet gives equal areas in equal interval of time. That means aerial velocity remains constant for a planet. Nothing but change in area by change in time is a constant, means area by time is a constant value. So here area by time, here area by time, here area by time, all will give same value. That means constant. Next, Kepler third law. According to Kepler third law, it details about the time period. That is why we are calling this is as law of periods. This law is also known as law of periods. Reason: the square of the time period of the planet revolving around the sun is directly proportional to cube of the semi-major axis of the orbit. Let me explain with a diagram. So here you can see a planet revolving around the sun in elliptical orbit, and here A is the semi-major axis. Now the time period means it is time taken for the planet to cover one complete rotation. So here that time of square value is proportional to cube of the semi-major axis. Once again, the square of the time period of the planet revolving around the sun is directly proportional to cube of the semi-major axis of the orbit. So here the time period means, I said already, it's the time taken to finish one complete rotation. Okay, so this one square value proportional to cube of the semi-major axis that he derived, I will derive in the next coming slide. Now here semi-major axis we can represent with A, or we can represent with X, or we can represent with R. So mostly they will represent with A, or R they will represent with R. So t square proportional to a cube, or t square equals to a constant into a cube. So for a particular planet, if there are two planets, then we can write this expression like this. For example, A and B are two planets. For the two planets time period square value and semi-major axis cube values, the ratio is equal. So Ta by Tb whole square equals to Ra by Rb whole cube. So this one only we can write like this. It is useful to solve numericals. In numericals they will give for two planets any details, means any three of quantities details they will give, they will ask other one. Out of 4 they will give 3 quantities details, other one they will ask to calculate. Next, Kepler third law proof, T square proportional to A cube, how they derived. So for that purpose they consider not exactly as according to his hypothesis derivation, they did not finish as according to the Kepler original statement, that is every planet revolving around the sun in elliptical orbit. For the convenience to show the expression in simple way, the derivation by taking the planet in circular orbit. Actually it is an elliptical orbit, but approximately to analyze this concept in simple manner, to derive with the simple steps, they consider approximately it is a circle. Okay, let capital M is the mass of the sun and small m is the mass of the earth, and a planet is for example revolving continuously around the sun in a particular fixed orbit. That means it is maintaining fixed orbit, means compulsory we should agree one point, that is as it is revolving continuously in the fixed orbit means everywhere the net velocity is same, means the planet is in equilibrium of forces. How many number of forces acting on the planet, that net force should be 0. So here due to gravitational attraction there is a centripetal force toward the sun, as well as due to the velocity of the planet outward force will be there, that we are calling as a centrifugal force. So centrifugal force due to the velocity in this direction and centripetal force due to gravitational attractive force, both will be balanced, the planet will make continuously same revolution. Okay, so that means as it is revolving, centrifugal force we can mention with respect to velocity, that is mv square by r, that is expression for centrifugal force. Now inward force means centripetal force, that centripetal force, or we can write gravitational attractive force, that is g mm by r square. Capital M is the mass of the sun, small m is the mass of the planet. So in general, so we can consider earth, so mass of the earth by the distance between them is r, then r square. Here distance from center of the sun to center of the planet earth. Now here the planet is maintaining continuously same orbit, same fixed path, means net force is 0. So two forces are there, two net forces equal means both are equal and opposite, so these forces are same, then only it can maintain that fixed orbit. So centrifugal force equals to centripetal force. So we can write like this, mv square by r equals to g mm by r square. Now both sides small m get cancelled and as well as r square get cancelled. So if you get cancelled, then the resultant expression will be like this, g m by r. So here r square get cancelled and m get cancelled, so that is why g m by r equals to, so here small m r get cancelled, only v square left out. Okay, so v square equals to g m by r. Now further, the speed of the planet is, so here our aim to identify the time period, so just we consider according to its velocity, we consider the force equilibrium concept and we developed one expression, but we want finally about time and distance. So time period we have to introduce, so that is why I am taking velocity here. So velocity in particularly actually continuously direction changing, so we can use the word speed. Velocity means it's a directional quantity, speed means it is a scalar quantity. So speed of the planet is v equals to 2 pi r by t. That means consider one complete rotation for Earth. For example, planet Earth finished one rotation, means with r radius it covered 2 pi r distance. So speed nothing but distance by time. So total distance covered is 2 pi r. So approximately I said they consider circular motion. Okay, so 2 pi r by, to cover one complete rotation, the time taken is called time period. So that is capital T. So 2 pi r by t. Now v, velocity expression already just now we got, that is v square equals to gm by r. So now instead of v, in this expression instead of v we can write to 2 pi r by t. So gm by r equals to, instead of v, 2 pi r by t. If you substitute 2 pi r by t whole square, so whole square means 2 pi whole square, 4 pi square r square by denominator t square. Now we want details about t square, so send this t square towards left and gm by r this side. So here denominator r, if you shift to right side it will go to the numerator, so it will become r square into r cube. So if you shuffle those quantities you will get t square equals to 4 pi square by gm into r square into r cube. So here 4 pi square constant, g universal gravitational constant is a constant, and capital M mass of the sun is a constant. So if you remove the constant we can write t square proportional to r cube, nothing but it is Kepler's third law. The square of the time period of the planet revolving around the sun is directly proportional to cube of the semi-major axis of the orbit. So here approximately semi-major, semi-minor both are same, so simply radius of the orbit cube. Okay. Next topic, acceleration due to gravity. So acceleration due to gravity means if you leave any body freely, then that will be attracted towards the sun, means attracted toward the center of the sun. Reason, that massive body will be attracted by the earth due to gravitational attraction. So due to gravitational attraction a body is getting the change in its velocity. If you just leave with zero velocity but continuously velocity increases, the change in velocity nothing but acceleration that is gained by the gravitational force. So that is why we are calling that acceleration gained by the body due to gravitation, we are calling as acceleration due to gravity, that we are representing with small g. So to analyze an expression for small g and to get the details about g, means what factors affecting the g of a particular planet. G value of a planet depends upon what factors. For that we need a mathematical expression, then only we can analyze what factors affecting the acceleration due to gravity. So for that purpose consider a planet. For suppose you can consider Earth. For example, radius of the Earth is, or radius of the planet capital R, and mass of the planet capital M, and there is a small massive body on the Earth surface that is very small in such a way that the distance from center of the planet to surface of the planet and the center of the massive body to center of the planet both should be same. Means here the small portion of the massive body negligible as compared with this radius. This is much bigger and this is very small. So two massive bodies are there. One is heavier planet, on that one small massive body. So due to the mass there is an attractive force towards the center. So that we can express in two ways. According to general Newton's second law, F equals to ma. So that is F equals to mg instead of acceleration g. But same according to Newton's law of gravitation, two massive bodies are separated by a distance r. Then attractive force between the two massive bodies is equals to g mm by r square. So these two forces on small m massive body, so both are same, we can equate. That means mg equals to g mm by r square. So both sides small m get cancelled, then g equals to gm by r square. So we can write g equals to gm by r square. With respect to this formula we can say the acceleration due to gravity depends upon mass of the planet and as well as inversely proportional to square of the radius of the planet. If the planet size is very small, For example, mass is as usual. Suddenly, for example, planet size reduced, that means G value increases. If M constant, R reduced means G increases. For example, the same planet radius same. For example, if you can increase the mass of the planet, for suppose practically not possible. If for example, if you increase the mass of the planet and radius constant, then also G increases. That means simply G, acceleration due to gravity, depends upon mass of the planet and as well as radius of the planet. So to attract much, a planet should have more mass, less size or less radius. Acceleration due to gravity in terms of radius and density. So in last expression what we derived, G equals to Gm by R square, means G in terms of mass and radius. Now we want to derive the expression in terms of density and radius, means instead of mass we want density. So for that purpose mass we have to replace. So for that we know density rho equals to mass by volume, nothing but mass equals to density into volume. So here V volume, nothing but it is a spherical body, so we can write volume of the sphere as 4/3 pi r cube. For suppose r is the radius of the planet, then mass equals to density into 4/3 pi r cube. Now instead of this mass, now we can substitute entire this expression, then mass term will be replaced. So in expression G, so we know that G equals to Gm by R square we derived. So in that, if you substitute instead of M what we analyzed from density, if you substitute instead of M mass, rho into 4 pi by 3 into R cube. Now R square cube get cancelled, in numerator only small r, Kepler will be available. So that is G equals to 4 by 3 pi G into rho into R. So according to this expression, acceleration due to gravity depends upon radius of the planet and as well as density of the planet, but both are proportional to each other. If density of the planet is high, that means acceleration due to gravity is also high. If radius of the planet is high, then also acceleration due to gravity is high. See in the old expression here, inversely proportional to square of the distance if mass constant. So here it's a triangular story. If one of one is constant, then only. So here G is proportional to R if density constant. If density is not constant, then we can't say. For example, if you stretch any planet, then the density decreases as R increasing. For example, practically not possible. Just imagine you are taking a very big air pump and you are injecting air into the earth core for suppose, and you are increasing the earth size as like balloon. You are adding air to the balloon, then balloon size increases, like that one planet size is increasing for suppose. As we are increasing the R, G value will not increase. Reason, as it is expanding, density decreases. So if density constant, then only as radius increases G increases, and as well as if radius constant, then if density increases, then only G increases. Reason, density increases means mass increases, as mass increases G increases. Okay, so if you did not understand, just go a little bit back and revise this audio, definitely you can understand. One more relation between G and M and rho, that is acceleration due to gravity in terms of mass and density. So previously we derived G in terms of mass and radius, afterwards in terms of radius and density, now last one in terms of mass and density. So for that, radius term should not be there. So to avoid radius term, so what we derived, that expression mass M equals to rho into 4 pi by 3 into R cube. Now we want only R, so that we can substitute directly in the expression G equals to Gm by R square. In that R we should eliminate, so that is why we can write R cube equals to, we can send 3 that side, then 3 into M, and remaining all will go to denominator 4 pi into rho. And further that R cube if you send that side, R equals to 3 M by 4 pi rho whole power 1 by 3. Further that r equals to 3m by 4 pi rho whole power 1 by 3. Now we applied square on both sides. In previous expression square not there. Now we applied square on both sides. Then r square equals to 3m by 4 pi rho whole power 2 by 3. I think now you can guess why we applied square on both sides. Reason, in the expression g equals to gm by r square, we have r square term. So that is why we did like this. Now further, if you can simplify, that is better. See here, whole power 2 by 3 if you write individually. So 3 by 4 pi is a constant, whole power 2 by 3, and m whole power 2 by 3, and the denominator rho whole power 2 by 3. So that whole power 2 by 3 we separated, means for entire constants 1 whole power, and individually for mass and individually for density. Now we know that g equals to gm by r square. Now instead of r square, if you substitute entire this term, then gm by, instead of r square entire term, that is 3 by 4 pi whole power 2 by 3 and m power 2 by 3 by rho power 2 by 3. Now this rho power 2 by 3 will go to the numerator. It is denominator to the denominator, we can shift to numerator. Let us see in the next step. Same as it is expression now. Now we can send the denominator to the numerator. So it will go to the numerator rho power 2 by 3, and as well as remaining terms also if you shift to numerator. So here 4 pi is denominator to the denominator. If you shift to numerator, then 4 pi by 3 whole power 2 by 3. G as usual. M power 1 and as well as this m power 2 by 3 also if you shift to numerator, then denominator m power 2 by 3 if you shift to numerator minus 2 by 3. So that is why m power 1 minus 2 by 3 into its denominator to the numerator as usual to the numerator. Now if you simplify further, m power only 1 by 3 will come. So therefore g equals to 4 pi by 3 whole power 2 by 3 as usual, capital G as usual. So m power 1 minus 2 by 3 nothing but 1 by 3. So m power 1 by 3 and rho power 2 by 3. So with respect to this formula, g proportional to m power 1 by 3 and g proportional to rho power 2 by 3. So generally this type of critical formulae useful to solve little bit higher end problems in JEE Main. So try to remember this one, so that if they mention the question in terms of mass, density and g, so directly by remembering this g proportional to m power 1 by 3, g proportional to rho power 2 by 3, we can solve the problem within less time. Next, variation of value of acceleration due to gravity with altitude, that means height. Variation of g with a particular height. For that purpose, consider a small massive body m at a particular height from the earth surface. So this is from earth surface, h is from earth surface or generally planet surface. So that planet mass capital M, planet radius capital R for suppose. Then the distance between the center of the planet to massive body we can express as, for example, the distance is r, small r, that we can write as r plus h according to the diagram. Now according to Newton's law of gravitation, this attractive force between the two massive bodies F equals to g mm by r square, small r square. Here distance between the two massive bodies is smaller, we consider, so r square. Now instead of r we can write r plus h, then the expression will be F equals to g mm by r plus h whole square. Now generally here m massive body is attracting towards the center of the planet. Now for example, we want acceleration due to gravity at a particular point. For example, here let g value at that place is gh, means g suffix h we are writing at a particular height we are mentioning. So g generally on the surface of the planet. We derived expression g equals to gm by r square, that is on the surface here, but we want acceleration due to gravity at a particular height. So there is a variation of g with respect to height, whether increasing or decreasing we want to know. So for that purpose, so here on this small m massive body according to Newton's second law, F equals to ma. If you apply, we can write F equals to mgh. So these two are attractive force on the massive body small m, means both are equal, we can equate. So if we equate the both, then small m will be get cancelled, then we will get a simple expression, that is gh equals to gm by r plus h whole square. So this is not the final expression, so this one we can use in general, but with comparison of the g at the surface, what is the value of g at a particular height? For that purpose, here in this expression small g is not there, means g on the surface, if it is there at a particular height, what is the value we can analyze. So with respect to the value on the surface, what is the value if you want to analyze, so here small g required. For that purpose, we can take r common in this expression. If you take r common, then in the bracket r, if you take common, then only 1 plus h by r not there, so denominator by r, but whole square as usual same. Just inside the bracket r I took common, then instead of r 1 plus h by r whole square. Now this whole square you can write individually for r and as well as 1 plus h by r. If you write separately, then it will be gh equals to gm by r square into 1 plus h by r whole square. Now gm by r square, nothing but here gm by r square, nothing but we know, which is equals to g, means acceleration due to gravity of the planet on the surface. The instead of gm by r square, we can substitute small g. So therefore you will get gh equals to g into 1 plus h by r whole square. So with respect to this expression, we can give one conclusion, that is, if h is approximately 0, height is not that much considerable one as compared with the earth radius. Earth radius is 6400 kilometers. For suppose the body is at 2 feet or 3 feet, nothing but 2 feet, nothing but 60 centimeter is negligible as compared with kilometer only. But here earth, for example, if you consider earth planet, then r value is 6400 kilometers, so negligible. So this is completely negligible, means gh equals to g, means at a height which is very small, then we can neglect the entire term, then gh equals to g. For example, if the height is very high, then it is a considerable one. So if height is high, then it is a considerable number and more than 1. So then with respect to that, g is bigger as compared with gh. So according to the mathematical expression, if h is very high, then the denominator value is more than 1. We are dividing with more than 1 value, means this gh value is less than g. So as we are going to the altitude or a particular height, g value is decreasing. This mathematical expression giving the information that as we are going to a particular height, g is decreasing. This one we can analyze in another way for small height. So small height means we can neglect, but even then if you want to give a clear picture, so we should mention like this: gh equals to, as usual expression I took. So here that whole power minus 2 means that 2 we can shift to the numerator and we can write whole power minus 2. And further, to analyze this expression, you should know one major point, that is, for example, a plus b whole square, we know is a fundamental formula, a square plus 2ab plus b square. Similarly, for example, instead of a, for example 1, instead of b, for example x, then 1 plus x whole square. So 1 plus x whole square, nothing but as like a square plus 2ab plus b square. So 1 square, nothing but 1, 2 into 1 into x, nothing but 2x, and x square, b square. So instead of that, x square. Now for our convenience, means here to give the approach to the formula what we derived so far, for that purpose, if x is very small, very small in the sense as compared with 1 also it should be very small, then only x square can be neglected. If x is very small, then x square term neglected. Reason, for example, x is 0.01 value, then x square value 0.0001, or simple example 0.1 is x value, whole square means 0.01, so it is decreasing. So if x only very small means x square is very small, so we can neglect. So if you neglect, we can write 1 plus x whole square equals to simply 1 plus 2x, means here the power came as coefficient, simply we can write 1 plus 2x. Now this is a special case. If x is very small, then only. If x is more than 1, it is not applicable. If x is very small, less than 1, then only. Now if it is 1 plus x whole cube, then also as like formula a cube plus 3ab square or 3a square b plus b cube, that formula if you apply, you will get a cube, nothing but 1 cube. Next 3ab 3a square b, 3 into a square term 1 square 1 into b value x, and next term 3ab square, so 3 into a into x square, and the last one b cube term nothing but x cube. I hope you understand. So here you got x square x cube terms also. What I said, x is very small, then x square neglected, x cube much dead less value, so we can neglect these two. So we can write simply 1 plus x whole cube equals to 1 plus 3x. Again we can analyze as a shortcut, the power came as quotient. So now we can generalize 1 plus x whole power n for suppose. Then we can write 1 plus x whole power n, simply we can write as 1 plus nx. The power will come as quotient if x is very small as compared with 1. If it is very less, we can write. Now come to our derivation. In that derivation, so this formula we are going to use what we derived so far, that is gh equals to g into 1 plus h by r whole power minus 2. So here as compared with 1, this is very small. I mentioned it is a case h value very small as compared with r. For example, for a planet Earth 6400 kilometers, and it is simply in 1 or 2 kilometers, that much low, then we can apply this formula. The whole power we can write as quotient. So here minus 2 we can write here. Then we will get gh equals to g into 1 minus of plus minus 2h by r. So this is the expression. Now with respect to this also we can say, at a particular height, if you substitute h value and r value, then it will be less than 1. So you are multiplying with g with less than 1, then only we are getting gh, means gh value is very small as compared with g. So generally small as compared with g, no need to say very small. So with respect to that formula, mathematical formula what we derived, we can say acceleration due to gravity decreases as height increases. Next topic, variation of value of acceleration due to gravity with depth. Means from the earth surface you are digging a hole and you are going towards the center of the earth. Then what about acceleration due to gravity? To find the variation of g, acceleration due to gravity with depth, consider a planet. For example, this is a planet with a particular surface. Let O is the center of the planet, and for example Kepler is the radius of the planet from center to the surface for suppose. And now from the surface to a particular depth, for example we digged a hole and we came up to here for suppose. Let the depth is d. So whenever we went up to a particular depth, then the remaining distance from the center of the planet to a particular this point, that will be remaining, that is r minus d. So now if you consider a point here at a particular depth, so from the surface of the planet to we went up to a particular depth, so here d distance depth, the acceleration due to gravity we have to find out. So let the acceleration due to gravity as g d, d indicates the depth, we have to find out that value. whether g increases or decreases. Let us see. So for that purpose, we know that acceleration due to gravity, that expression is g equals to gm by r square. This is in terms of mass and radius, but we know the same acceleration due to gravity in terms of radius and density. We derived that expression, that is g equals to 4 pi by 3 into capital G into rho into r. So this is the acceleration due to gravity on the surface, so with radius r for a particular planet, means here g value, but we want at this point, so that means radius value r minus d. So if you substitute instead of r minus d, then the g will be gd, means acceleration due to gravity at a particular depth, that is 4 pi by 3 into g into rho into r by r minus d. Now further, if you take r common, then in the next step same expression. Now if you take r common, then here only 1 minus d by r. So now if you see the term what is there in front of the bracket, this is nothing but g on the surface. So instead of that entire total expression we can write g. So therefore gd, acceleration due to gravity at a particular depth, equals to g into 1 minus d by r. So with respect to this formula we can say, as we are going to a particular depth, then the total value in the bracket will be less than 1, and that if you multiply with g, we are getting gd, means the gd is less as compared with g, means acceleration due to gravity decreases as we are going to a particular depth. The value of acceleration due to gravity decreasing as we are going to a particular depth. And one more point, if you go up to the center of the earth, then if you go up to center of the earth, means d value equals to r. So if d equals to r, then r by r 1, 1 minus 1 0, means acceleration due to gravity at the center of the earth or center of the planet is 0. Null points in gravitational field. Null point means it is a point at which the resultant gravitational force is 0. Resultant gravitational force means you can consider in a gravitational field one point. There, if you keep any massive body, on this massive body net gravitational force should be 0. Consider a diagram, for example m1, m2, two massive bodies. So these two massive bodies definitely will attract each other due to mutual gravitational attractive force. But if you introduce any other massive body, for example at a particular point, then the force due to m1, for example here m1 is smaller and m2 bigger, then very near to m1 massive body, that attractive force, and even though distance is little bit high due to heavier mass, this m2 also can attract, so the net gravitational pull will be 0 at a particular point. For example, if both are same massive bodies, definitely at the center the net gravitational force will be 0, but here we consider just a little bit uneven, so near m1 the gravitational force will be 0. For example, if you are very near to m1, the domination of m1 will be more, m1 will attract with more mass. As we are going away from m1, the attractive force due to m1 decreases, and as we are going towards m2, attractive force due to m2 increases. So at a particular point definitely the force due to m1 and force due to m2 will be 0. That point we are calling as null point. Why? Because net gravitational force 0. So to get the distance where the gravitational force 0, that point null point, so to locate, to identify the null point from the smaller massive body, so consider the distance between the two masses as for example smaller. If you consider this is as smaller distance, and from the null point m1 is at a distance x, then the remaining distance is r minus x. And for suppose here there is a small massive body m, on this mass the net force is 0. So force due to m1, force due to m2 both are equal and opposite. So we can write F1 is gravitational pull due to m1, that is F1 equals to g m1 m by x square. x is the distance, so that is why denominator x square. Now similarly, that attractive force due to m2, let it be F2, equals to g m2 m by the distance is r minus x, so that is why r minus x whole square. So here, according to null point concept, net gravitational field, gravitational force should be 0. So net force 0 means both are equal. F1 equals to F2. Equate the both. So these two right hand side terms equal. If you equate the forces, you will get g m1 m by x square equals to g m2 m by r minus x whole square. So both sides small m get cancelled, capital G get cancelled. If you get cancelled, then the remaining expression will be m1 by x square equals to m2 by r minus x whole square. So we want expression for x, that is null point from smaller massive body, how much distance. So for that purpose, if you shuffle the expression, you will get the expression for x. So here r minus x whole square, if you shift towards left side and m1 towards right, then you will get r minus x whole square by x square equals to m2 by m1. Now further, here r minus x whole square as well as at denominator also x square, so whole square we can write, that is r minus x by x whole square equals to m2 by m. Further, that square you can shift this side, then it will be square root, so the expression will be r minus x by x equals to square root of m2 by m1. Further, this is the x is common for both the terms, so if you write individually, then you will get r by x minus x by x nothing but 1 equals to square root of m2 by m1. So we want expression for x, so that is why shift this minus 1 that side, then you will get r by x equals to square root of m2 by m1 plus 1. Now the total term we can shift towards the left side and the x we can keep right side, then we will get x equals to r by the total right side term we can write at a denominator, that is square root of m2 by m1 plus 1. So here what is x? This is the distance of null point from smaller massive body. So this is the shortcut expression. So with this easily we can solve the problem regarding null point. So for that, let's go for an example. Two massive bodies. So let question point of view. Two masses 2 kg, 8 kg are 12 centimeter apart. Find the distance of the point where net gravitational force is 0 from the smaller mass. So we derived already the expression. So we know the formula, x equals to r by square root of m2 by m1 plus 1. So first write the given data. So given m1 2 kg, m2 8 kg, r distance between them is 12 centimeter. So here mass is in kg, that is mk system, centimeter is in cj system. Even then no need to change. Reason, here m2 by m1 is the ratio, so that kgs will be get cancelled, nothing but there is no unit. So with respect to r unit, x unit will be decided. If you convert this one in meters, x will be in meter. If you keep r as usual as a centimeter, then x value also will come in centimeter. So if you substitute these values in the equation, r nothing but 12 by square root of m2 value 8, m1 value 2 plus 1. Now 8 by 2 nothing but 4, so that is why 12 by square root of 4 plus 1, root 4 nothing but 2, so that is why 12 by 2 plus 1. So 2 plus 1 3, so that is why 12 by 3 nothing but 4 centimeter. Next topic, gravitational potential energy. Gravitational potential energy of a system of two masses is defined as the amount of work done in bringing these two masses from infinity to their respective places. It is defined as work done. So here work done is numerically equals to potential energy of the two masses. So here to keep two masses at a particular distance r, we did certain work. That work is the potential energy between the two masses, means the work will store as potential energy between the two masses. So as according to work energy theorem, the work is nothing but energy. So here in terms of potential energy. So for that purpose, consider two massive bodies. For example, M1 is at a position O and M2 we moved from infinity to a particular point P for suppose. So for that we have to do certain work done. So the work done nothing but force into displacement. So that entire displacement we can't analyze. Why? Because we defined from infinity. So that is why we are taking the help of integration. So here integration means we are taking the work done in bringing the massive body M2 from A to B. So that is dx, the distance we moved. That work done is small work done, for example dw. Then if you add small work done like this from infinity to up to P, then you will get the entire work done. Means we are calculating the work done for a small displacement, and by taking from infinity to R we will get the entire work done. Means here we are taking the integration, means we are adding all such work done to get the net work done. So for that purpose, for suppose initially the M2 massive body is at A. At that time the distance between M1 and M2 let x, then x distance M1 M2 are there. So there is a force, that is gravitational force. So due to the gravitational force those are coming towards each other. So for example M2 is coming towards M1, then the work done due to that gravitational force we can express as F equals to g M1 M2 by x square at a particular point A. Now we moved a small distance, it's a very small, in such a way that x is we can consider as it is same. So dx distance it moved that much small, infinitesimally very small. Then the work done to displace dx distance we can write as work done dw equals to f into dx, means actually f bar dot dx bar. So it is a dot product between force and displacement, nothing but f dx cos theta. Here force is along M1 and as well as displacement is also along M1. So both are in the same direction, nothing but theta 0. So cos 0 value 1. So we can write as dw equals to f into dx. So the work done in bringing the M2 massive body from A to B, that is dw equals to f dx. Now we want work done from infinity to up to r distance. So for that purpose dw instead of f we can write g m1 m2 by x square into dx. So dw equals to f dx, instead of f we substituted. Now we want entire work done. To get the entire work done, that is w equals to integral dw. So here integration from infinity to r distance, if we add all dw work done we will get the entire work done. So here we are taking the help of integration. So in integration formula, for suppose general basic formula if you consider, that is x power n dx equals to x power n plus 1 by n plus 1. This is the basic formula in integration. So this formula I am going to use. So this is based on integration. Similarly same x power n differential formula is also there. We have to remember these two. So x power n, if you differentiate, that is n into x power n plus 1. So small confusion will be there. So that is why I mentioned both here. We are going to use this expression integration. So best example wise, if you consider only x square, if you integrate with respect to dx, then if you apply this formula, x power instead of n now 2, so 2 plus 1 by 2 plus 1, so that is x cube by 3. For suppose if it is x power minus 2, then x power minus 2 dx equals to, so x power that instead of n now minus 2, so minus 2 plus 1 by denominator also minus 2 plus 1. So minus 2 plus 1 means minus 1. So minus at numerator or denominator both are same, so I am writing at numerator, so minus 1 by x. So here x power minus 1 will come, that if you write at denominator it will be x power plus 1. So Finally, on integration of x power minus 2, you will get minus 1 by x. So this formula we can use here. Why? Because 1 by x square nothing but x power minus 2. On integration, you will get minus 1 by x. So if you apply, first g m1 m2 constants, if you write outside, then integration for only the variable x. Here x is the variable, so integral infinity to r x power minus 2, at denominator x power 2, so at numerator x power minus 2 dx. So x power minus 2 dx nothing but 1 by x, so that is minus 1 by x. So minus g m1 m2 into 1 by x, limits infinity to r. So here it is upper limit, next lower limit. So if you substitute the limits, you will get the expression like this. First upper limit r, so 1 by instead of x r, next lower limit instead of x infinity. So 1 by infinity 0, so that is why you will get the expression as minus g m1 m2 by r. So this is the work done to keep two massive bodies at a distance r, that is minus g m1 m2 by r. Now this work done is stored in the particle as its gravitational potential energy, what I mentioned in the definition. So therefore gravitational potential energy of the particles or massive bodies we can express as U equals to minus g m1 m2 by r. So this is the expression for gravitational potential energy between the two massive bodies, or for the system of two massive bodies, gravitational potential energy formula. Next topic, escape velocity. Escape velocity, it is the minimum velocity required for a projectile to escape from the surface of a planet, or to escape from the gravitational influence of a planet. So that velocity we are calling as escape velocity. Why? Because if you can throw with this velocity, the particle cannot come back to that planet surface, or cannot come back to the earth surface if you throw from the earth surface with this minimum velocity. Now I am going to derive an expression for this escape velocity for the earth. With respect to that, we can get the value of escape velocity to the planet earth, or in general for any planet. So for that purpose, consider a planet of mass m, for example earth mass m and radius r. On the earth surface, for example, there is a small massive body m is projected with a minimum velocity v, that is escape velocity for suppose. If it is the escape velocity, it cannot come back, means initially it is having the potential energy. For example, if it is at rest, that time it is having only potential energy. Now we gave the equal amount of kinetic energy, so the total potential energy should be 0. Like that we gave the energy, then we can express like this. So total potential energy and kinetic energy sum is 0. So here both are equal but sum 0. Reason, here the potential energy is having negative sign. Reason, both are inattractive. So massive bodies attract each other, so that is why for the gravitational potential energy we got negative sign. So the sum of two energies, already it is having negative potential energy. If you add kinetic energy, the net will be 0. So then it is free from the gravitational field, or it's free from the potential energy. Now if you substitute both the values, so here kinetic energy equals to minus potential energy. If you substitute both, kinetic energy nothing but half mv square we know, so half mv square equals to minus into, actually potential energy equation is having minus, so minus g mm by r. Now minus into minus plus, and as well as m get cancelled, then you will get the same expression. Now masses get cancelled, then the escape velocity Vg equals to square root of the 2 went to right side, then 2gm by r whole root. So this is the escape velocity expression, but this one we can mention in terms of acceleration due to gravity of the planet also. So for that purpose, to get the expression in terms of g, multiply this expression inside the root with r and again divide with r. So multiply with r, divide with r, then we can get the term in terms of g. So multiplied with r and divided with r, then r into r, denominator r square. Now gm by r square, that our easy known formula, gm by r square nothing but g. So instead of gm by r square we can substitute acceleration due to gravity of that planet. So we will get escape velocity ve equals to 2 into g into Kepler. So here escape velocity depends upon acceleration due to gravity of the planet and as well as radius of the planet. If you substitute those values, for example for Earth, g value 9.8 average value meter per second square and radius of the Earth average value 6.4 into 10 to the power of 6 meters. If you substitute both values in the above equation, then you will get square root of 2 into 9.8 into 6.4 into 10 to the power of 6. So if you simplify, you will get on the surface of the Earth escape velocity equals to 11.2 kilometer per second. So it's a value kilometer per second, not per hour. So be careful. So within 1 second, if you can throw the particle 11.2 kilometer per second velocity, then definitely the particle cannot come to the Earth's surface. It has to travel in such a way that within 1 second it has to travel 11.2 kilometer distance. Then the particle cannot come back to the Earth's surface. Escape velocity of a body from certain height above the surface of a planet. So for that purpose, first consider what we derived, escape velocity square root of 2 gm by r in terms of small g, that is ve equals to square root of 2 gr, but now we want at a particular height. So on the surface of the planet or Earth, these are the escape velocity expressions, but at a particular height the distance will be r plus h. For example, from the Earth surface the point is at a height h, then at a particular height the distance from the center of the planet will be r plus h. So now instead of r, now r plus h. So it is a simple expression. Instead of r, if you substitute r plus h, then you will get escape velocity at a particular height. So that is 2 gm by r plus h, or r, which is equals to square root of 2g into r plus h. This is the expression for the escape velocity at a particular height. So here that escape velocity is independent of mass of the body. For any massive body, acceleration due to gravity depends upon the planet mass and the planet radius, not depends upon the mass of the body. So any massive body, if you can throw with 11.2 km per second velocity, it cannot come back to the planet surface or Earth surface. Next topic, orbital velocity. So a body has to rotate around a planet, for suppose Earth, it should have a particular velocity. Then that body can rotate. Reason, the gravitational pull between the body and the planet, and due to velocity outward centrifugal force, both will be balanced, net force 0, then the body can rotate freely around a particular orbit. To rotate in that orbit, it should have a certain velocity, that is called orbital velocity. In simple way, orbital velocity definition is velocity of a satellite moving in the orbit is called orbital velocity. So to move in that orbit, how much velocity required, that we are calling as orbital velocity, and in simple manner the velocity of the satellite moving in that orbit, that we are calling as orbital velocity. Now expression for orbital velocity. So for that purpose, so consider a diagram. A satellite, a body of mass m, is rotating around a planet Earth, for suppose planet mass capital M, planet radius r, Earth radius r, and the body or satellite is rotating around the Earth with a particular height. So from the surface at a particular height it is rotating. So then here the planet has to rotate, for that it should have certain velocity, that is orbital velocity. For example, it is maintaining that orbital velocity, then that outward centrifugal force and due to attractive force, inward force, centripetal force, both should be balanced, then only it can follow that orbital path. So here, according to that condition, if it has to rotate compulsory, it should satisfy that condition. So here, radius of the satellite we can mention as r plus h, and further that centrifugal force, that is outward force, that will be mv square by r with respect to its velocity, and r nothing but r plus h according to the diagram from the center of the planet to the center of the satellite or body, that is r plus h. So this is the force on the body which is rotating due to its velocity. At the same time, inward force will be there, that is the centripetal force due to acceleration due to gravity, that is g mm by distance square, that is again r plus h whole square. Here these two forces are equal and opposite, so that is why both get cancelled. It is following same as it is orbital path. So both forces are equal. So if you equate, you will get m v naught square by r plus h. Here v naught we are using symbol reason. Here v is the velocity, v nothing but orbital, so orbital velocity indication. So m v naught square by r plus h equals to g capital M small m by r plus h whole square. Now here small m get cancelled, and further if you get cancel small m and denominator r plus h both sides, then you will get v naught square equals to gm by r plus h. Now further, if you send square right side, then you will get v naught equals to square root of gm by r plus h. So this is the expression for orbital velocity of the satellite at a particular height. Now different cases we can discuss. So according to this formula, we can make one statement first, that is orbital velocity is independent of mass of the satellite. Irrespective of the mass of the satellite, that depends upon only mass of the planet and the distance. It is independent of mass. For any massive body, the orbital velocity will not depend on that mass. And further, if you consider the particle or satellite or massive body is very near to the surface of the planet or surface of the earth, that means h value very small, then that h we can neglect as compared with radius of the planet, then v naught we can express as square root of gm by r. So this is the expression. So this is one expression at a particular height, and this is the expression very near to the planet surface or earth surface, but still we can modify this equation, means we can express in terms of small g. So for that purpose, to get the orbital velocity expression in terms of small g, so multiply the equation with r and divide with r inside the root, then we will get gm into r by g into r square root of. So now at denominator r into r square, so then he will get gm by r square into r. Now we know that gm by r square nothing but small g, so therefore orbital velocity v naught equals to square root of gr, that is very near to the planet surface or earth surface. We know that escape velocity equals to square root of 2gr. Now we can get the relation between orbital velocity and escape velocity. So for that purpose, just divide this equation into two terms, that is root 2 into root gr. So if you write like that, escape velocity ve equals to, will get root 2 into root gr, but root gr nothing but v naught, so therefore escape velocity equals to root 2 into v naught. So with this expression we can say that escape velocity is greater than orbital velocity. So now next topic, artificial satellite. So before going to learn the details about artificial satellite, first satellite. Satellite means it is an object that moves around a large object. So the body which is rotating around any particular massive body, we can call that is as a satellite. Simple example, earth is revolving around the sun, so earth is a satellite. because it moves around the sun. Similarly, moon is also revolving around the earth. So the moon is a satellite because it is moving around the earth. So here earth and moon both are satellites. Those we are calling as natural satellite. Why? Because naturally those are existing. Nobody forced those bodies to rotate. But if you can arrange any massive body which can rotate around a particular massive body, then we are calling those as artificial satellites. By force we are designing. So that is artificial satellite. So artificial satellites are man-made bodies that revolve around the earth. They are used for multi-purpose like communication, weather forecasting, remote sensing, etc. So nowadays we are using these artificial satellite in communication, and as well as mostly we are using for weather forecasting. Those are giving very good information to save many human lives. 1 or 2 days before only about the cyclone and what is the wind velocity we are going to get at the coastal corridor, they are giving the information along with wind direction also. So with respect to that we are able to save ourselves, so whenever we are getting the cyclone effects. So artificial satellites are very much useful for us. Let us see further details. These we divided as two categories, means according to the usage wise: geostationary satellite, polar satellites. So to send these satellites compulsory there is a requirement of vehicles. So let us see those vehicles we are calling as GSLV, PSLV. So GSLV means geosynchronous satellite launch vehicle, and PSLV nothing but polar satellite launch vehicle. So PSLV, GSLV, these two vehicles are important one to send the satellite in a particular orbit. So actually geostationary satellite in a particular orbit, polar satellite means it is having specific purpose either in a particular orbit or we can send to study about other planets also. Geostationary satellite means if the time period of revolution of any artificial satellite is equal to the time period of rotation of Earth, then such a satellite is called geostationary satellite. So here geostationary in the sense with respect to Earth the satellite is at rest. For that compulsory it has to rotate around the Earth within 24 hours. Earth is taking 24 hours time to rotate about its own axis. Similarly the satellite also has to finish the same rotation around the earth within 24 hours only, then only with respect to earth it will be at rest. So you can see one blue orbit. If the satellite is revolving in this orbit within 24 hours, so earth also will rotate about its axis within 24 hours, it will cover the total path. Similarly the satellite also will cover the entire orbit within 24 hours. So with respect to earth the satellite will be at rest, nothing but it's a geostationary satellite. But actually in deep if you observe the axis of rotation of the earth, it is tilted little bit and it is rotating about this axis by making an angle 11.5 degree. So with respect to that if you release any satellite in such a way that it is maintaining the same stationary sense by making an angle, then that satellite we are calling as geosynchronized. So with respect to earth axis of rotation we arranged the satellite in such a way that it is at rest with respect to any point on the earth at the equator. So we are calling such satellites are called geosynchronized. Next, condition for stationary means geostationary satellite. It should maintain some condition, then only we are calling that is as a geostationary satellite. The first one is height of the orbit above the earth surface is about 36,000 km. Then only with respect to earth, three satellites can cover the entire globe, nothing but earth, and they can monitor entire earth and they can give the complete information about the Earth every time. So 3 satellites can cover with a 36,000 kilometer range. So that is why that height should be 36,000 kilometer. Next, the orbit of satellite must lie in the equatorial plane of the Earth. Then only the perfect geostationary sense will come. So it has to maintain the same. The orbit of satellite must lie in the equatorial plane of the orbit, and as well as the sense of revolution must be same as that of rotation about its own axis. So if Earth is rotating, so Earth rotating from west to east, so that is we are observing sun rotating from east to west. So Earth rotating in which sense, the satellite also has to rotate in the same sense, then only both will be at rest. With respect to Earth, the satellite should be at rest, then only it is a geostationary. For that, in which way Earth is rotating, in that manner only the satellite has to rotate, means must move from west to east. So Earth is moving from west to east, so the satellite also has to move from west to east in the equatorial plane of the Earth. And the time period of revolution of the satellite must be equal to time period of the Earth rotation, that is 24 hours. It's also compulsory. And last one, the orbital angular velocity of geostationary satellite must be same as that of the Earth. Means the satellite covering the total path per second, how much angle is covering. So Earth also has to finish the same. So in which way Earth covering the theta, here the satellite also has to cover the same angle. Means here angular velocity means rate of change of angle. So the rotation of angle of Earth and as well as the satellite should be equal. Next, uses of geostationary satellite. Those are for the study of upper layers of the atmosphere. So we can study the atmosphere and we can give complete information about the earth and wind movements and all. Next, for forecasting the changes in atmosphere and weather. So clear weather report we are able to give accurately with the exact wind velocity. It is possible now due to these geostationary satellites. Next, for finding the size and shape of the earth. So perfect positioning. So total earth clear size shape information we can get. Not only that, we can study the entire earth for investigating the materials and ores present in the earth's crust. That means we can study completely about earth and we can get the details about minerals and as well as ores, where those are located, and as well as the mostly major contribution, that is for transmission of TV signals. So for communication, geostationary satellites are very much useful for the mankind. And much more important one, we are using geostationary satellite for GPS, for that is for navigation, means including the GPS, global positioning system. So exact navigation we can do, and as well as the position of any particular person easily we can trace out, or we can give the address wherever the people are there. So with respect to GPS system we can trace out. So nowadays many people are using Google Map by using GPS system only. So geostationary satellites are having vast uses. Last, for space research also these are useful. So we are sending different satellites to different planets and we are studying about those, and we are sending satellites to moon, we are calling Chandrayaan projects. So with respect to that we are able to study the details about the moon and as well as different planets. Mongolian project, we are sending the PSLV satellites and we are going to get the details about those planets also. In future we are sending many satellites and in future we will get much more details about those planets also. So here last about polar satellite. Polar satellite is a satellite whose orbit is perpendicular or at a right angle to the equator. So in case of geostationary satellite, the satellite will revolve in the plane of equator, but here polar satellite will move perpendicular to the equator. we can define in another way also, that is, a satellite passes over the north and south poles as it orbits the Earth. So geostationary satellite continuously will revolve around the Earth along with the Earth, but it will rotate from north to south, so it's completely different from a particular height. That height is also, it can be any height from the Earth. Typically we are using 500 to 800 kilometer only. And time period also, the time period of polar satellite is around just 100 minutes. Its time period is about 100 minutes, so as a result it crosses any altitude many times within a day. So it has to rotate faster, like that we arrange, so within fraction of minutes it will cross number of altitudes. So we are using this one for many purposes like defense and different cases.